Hello there. One of the most important assumptions we make when dealing with our data and conducting statistical analysis is the assumption of normality. What do I mean by that? Well, what I mean is that when we look at our data, we graph it, we're expecting, or our statistics are assuming, that we have a normal distribution, a normal bell-shaped curve with the majority of the values being clustered around the mean. This was an okay drawing. You'd probably need to bring this out a little bit more like that. And then we've actually got a pretty good version of this, a pretty good normal distribution, ignoring my little flying mark here. So if we can tell if we have an abnormal distribution from looking at it, because if we looked at a negatively skewed distribution, you can tell that that's not normally distributed, but because we need to be able to quantify the difference to justify our response to an atypical distribution or a non-normal distribution, non-bell-shaped distribution, we need to be able to quantify exactly how different it is and use that as justification for our actions. So there are two ways we measure this. The first is with skewness. So this here is a skewed distribution. The mean has been pulled down due to large outliers over here. If we were looking at a positive distribution, like income, we could see that we have an issue here where people like Bill Gates, who make a whole bunch of money, who are worth a lot of money, pull our mean way above the average income, that they're above 3 standard deviations from the mean, so it would be possible to justify excluding them, but we'd need measures of skewness to help justify that. We'd look into that, and then we'd need to be able to say, well, yeah, he is 27 standard deviations above the mean, so let's go ahead and cut him so we can look at the population as the average population as opposed to the entire population. Let's go ahead and mark this as a negative skew. And then talk about how we calculate this. So for skewness, we're going to use a very familiar calculation. In fact, I think you'll recognize the first part of it. We have the sum of x minus mu, looking familiar, isn't it? Then we come to the wacky part. Instead of squaring this, we're cubing it, and then we're going to divide by n times the standard deviation cubed. So, important formula. A lot of this we're familiar with. It's just going to be a little bit different. Let's go ahead and use our old data set. So we're going to use our 3, 3, 5, 8, 10, and 13 with a mu of 7. We're going to have 5 different steps for this process. The first step is we're just going to go ahead and fill in our numbers. So we're going to have 3 minus 7 cubed plus 3 minus 7 cubed plus 2 minus 7. Ooh, got those numbers mixed up. 5 minus 7. I'm thinking a step ahead here. 5 minus 7 cubed plus 8 minus 7 cubed plus 10 minus 7 cubed plus 13 minus 7 cubed. And all of that is over 6, because that's how many numbers we have, data points, times standard deviation, which was 3.7 cubed. Let's go ahead and bring some of this in to differentiate between our steps, make it easy to follow. Step 2, we're going to go ahead and deal with our parentheses here. So we're going to end up with negative 4 cubed plus negative 4 cubed plus negative 2 cubed plus 1 cubed plus 3 cubed plus 6 cubed. And all of that is going to remain over 6 times 3.7 cubed. Moving on to our next page, and step 3, we're going to deal with our exponents. So we're going to end up with, and before we get there, it's important to note that when we're dealing with cubes, we're not going to be negating our negative signs like we do when we're squaring something. We're going to end up in a space where we have our negatives over here. So we're going to end up with, let's see, I don't remember how to calculate cubes on this, so we'll go ahead and use the squares from yesterday and then just multiply by the number again to get our cube. So we had 16 times 4 is equal to 64, and I just need to remember that that's negative because our original sign was negative. So we're going to have negative 64 plus negative 64 plus, let's see, negative 4 times 2, or rather 4 times negative 2 is negative 8, so plus negative 8. 1 stays as 1, plus 1, plus 9 times 3 is 27, plus 36 times the original 6 is equal to 216. And all of that is over 6 times, let's see, what was 3.7 squared? Well, we haven't done that before, so we're going to have to calculate that from scratch. So 3.7, we'll square it, gives us 13.69 times 3.7 again is going to give us 50.653. We dropped the 3 because I only want to deal with 2 digits. And there we go. Now, step 4, I'm going to go ahead and add our numerator and multiply our denominator. This is going to give me, let's see, that makes negative 128. We're going to add negative 8. So that equals a negative 136 plus 1 plus 27 plus 216 is equal to 108, so a positive number. Over, I'm going to take 6 times 50.65 is equal to 303.9. We'll just go horizontally for step 5. Go ahead and put another color on here too. We're going to end up with 108 divided by 303.9 is equal to 0.36. This 0.3553 rounds to 0.36. So there we go. We ended up with a positive value, which means we have a slight positive skew. If we had a negative number out of this, we'd end up with a negative skew, or rather, it would indicate that we have a negative skew in our data. So, there you have it. That's how we calculate skewness. Let me know if you have any questions about this process or anything else what you'd like me to cover next. I will see you in the next video where we're going to take a look at the other measure that I alluded to at the beginning, which is kurtosis.